I'm going to break this up so that's actually nice and easy for you to go back over to here. Okay? So, open up this file, right? I'm a big fan of video games, if you can't tell. And I do like, the odder the video game is, the better. Like Gus, I love Slay the Princess, I love World of Horror. My favorite game so far, though, this year is RimWorld. I'm really enjoying that.
I gotta get back into that game, actually.
I've been playing with Combat Extended. It's been an experience. Okay.
Especially with all the mods, man.
That is, yep. So what we do over here in order to get this in, by the way, is, so what you want to do is unzip this zip file with Hunt on it, okay? Right? And then what you're going to do is you're going to take this, you're going to drag this into your SRC folder, right over here. And then that's it. So that's the main thing you need to know, dragging all these files into SRC. Got it? So for this homework, you're given a bunch of files, and that might look very intimidating. Okay? Probably does look intimidating, but that's okay. So, but the main thing is dragging this into SRC. If you have issues getting this set up today, I will be around to help you. Right now, it's more about seeing what this program does. So what this is that we've got two main classes. I'll show you the first one, which is called Rabbit Hunt. And we can just simply run it. This is a fairly old program. It's more than 20 years old, but it's awesome. I love it because it's a very good assignment. One might even say it's nifty. It comes from Nifty Assignments. So I get a grid here. If you're running on a Mac, you might get a blank screen. It's fine. And what you get is this diagram, right? And once again, this is a classic, well, as we say, MCV, Model Control View. Basically, it's a way of doing a GUI. And as you can see, the program's already going to start by working. And what it is that we've got a fox in red, and then we've got a rabbit in yellow/gold. The object of the fox is to eat the rabbit because it's hungry, and that's what foxes do. The object of the, he's getting away. The object of the rabbit is to not get eaten, which he fails at quite often right now. The rabbit needs to survive 100 turns. If the rabbit survives 100 turns, he wins. A turn, by the way, just simply so that we can be very clear about this. Reset. Step. A turn basically is the rabbit taking his turn and then the fox taking his turn. I'll talk about what those yellow things are, this yellow diagram is in a bit. Right? But it's a turn-based game. They're not making their turns at the same time. Okay? So that's the Rabbit Hunt. That allows you to see the results of what you code. You'll be graded based off of the grader, which is very helpfully named here. The grader takes your strategy, runs it, and gives you a grade. Here it says the rabbit escapes 3 times out of 300, or 1% of the time, resulting in a grade of 10 out of 100. The grade is actually a bit more complicated than that. You'll be getting 20 points added to that for a total of 120, just simply to help curb and cushion the grade, because you can't really get 100% on this one. So, but anyway, the way this grade over here is calculated is that we take the square root of this number, your survival rate, multiply that by 10. So an 81% survival rate will get you a 90. It helps you get. So this helps that even if you get like only a 50% survival rate, you'll still be getting a passing grade on this one. And so that if you have big tangled spaghetti code, it doesn't really go to waste so much. That being said, you don't really need a big, as I showed David a few nights ago, you don't really need a big tangled spaghetti code for this one. A survival rate around 90% takes about 10 lines or so. So let me go ahead and tell you what your objective is. So you have a bunch of classes here. They're not here for you to modify. The only class you're allowed to modify is the rabbit. And this is why it's an object-oriented programming assignment, because a rabbit is an animal. So it gets to use all of those animal methods that the fox does as well. it's got the constructor already set up for you. And what you want to do is you want to modify decide move. Decide move currently, right now, is this. It says, where am I going to, it's going to return an integer representing a direction. North is, by the way, is 0, 1 is northeast, 2 is east, but we don't have to remember that because model, as I'll explain, has all those things already plugged in. Model.e gives you east. Not that you're going to be using specific directions much anyway, as we'll see. But basically what this is saying is that it's return something random between the model.min direction and model.max direction. In other words, just move randomly. You can see how this does not lend itself very well for survival. You can also tell it to just not move by using model.stay. This is all documented in the PDF. But now let's go over the parts that you don't really need to focus on for a second, which is we've got so this is a model view controller. The way this works for GUIs is that basically you've got, when you have a GUI, a graphical user interface, a good way to think of it is that you have the model. You have the internal logic that's going to be displayed to the user. Okay? The way the program works. When we run the grader, we're only just using the model. The view and the controller were completely unnecessary, right? It was running through the program without us looking at it, right? The view is what we see here. It's this game over here that we see. That's the view. The controller is this stuff, the windows and the buttons and stuff that we press to run the game. So when I hit reset or run, that's the controller. None of this, the view, the controller, none of that has to be programmed. It's already there for you. What you're going to be doing is changing part of the model, which is the rabbit class, right? You have the big model class, which represents a whole bunch of stuff and a bunch of useful methods that we're going to go over. But then you've also got the rabbit himself. Okay. So what do we need? So let's go ahead and take a look at our adversary, shall we? The fox. Once again, you're not going to really want to, you can't really change any of this code in here. But the other piece of warning I want to give is that a lot of students, they look at this fox and they're going to like, okay, I'm going to do exactly what the fox does, but opposite. That's generally the wrong strategy. There's only a few useful things to note from the fox and grab for your own program. I would say a good goal for, let's see, how much time do we have?
We're still good on that.
Okay, a good goal for today / beginning of tomorrow's lab would be if I see the fox run directly away from it screaming. This is not a good survival strategy, but it will get you to the point where you can say, I'm understanding how this is working, and I understand how to control this. Okay, so let's go ahead and see. The fox, the way he works is that he says, have I seen the fox this turn? Sorry, have I seen the rabbit this? Sorry, have I seen the rabbit at all? No. Have I seen the rabbit this turn? No. And then keeping track of the distance and the direction and the current direction. Okay, blah, blah. Set this guy up. Decide move. So this is a decide move function. So he's an animal, so he has a decide move function that he's overriding as well. So, can I see the rabbit now? He sets it to false. Then he has this for loop. For int I is equal to model.min direction, which if we hover over that, that should tell us that it is 0. I is less than or equal to model.max direction, which if we hover over that, it will say that is 7. 7. Notice that it's less than or equal to. This is probably the most common, this is one of the other common mistakes I see here, or typos, I should say, where students will do a less than or equal, they'll do a less than by just kind of out of habit rather than a less than or equal to when they do this line to look in every direction. I++. So go through all these possible i's, and we say if look I equals model.rabbit. So in other words, we've got this for loop that iterates from 0 to 7, each representing a direction, and then we use a look function that's built into animal to look in a direction. What look does is that it returns a numerical value that can be translated into rabbit or fox or bush, and it will say, hey, what am I seeing in this direction? So when we run this program, this rabbit hunt, let's go ahead and see. We can actually see the look function occurring, which is we use step. And we can see that was the yellow line that was being sent out by the fox. That's the look function. So it's looking in each of the 8 directions that you can in a grid. Okay? So it's basically saying I see a lot of bushes, I see a lot of wall, but I don't see a rabbit. And so he keeps doing this until he sees the rabbit. Right? If he sees the rabbit, his behavior will change. Notice that it looks like he should see him, but again, it's a grid, so no, didn't see it. Sometimes the rabbit just gets plain lucky. But no. And then he gets eaten. Okay? So if I see the rabbit, he says, you can actually do this nifty multiple assignment statement where he sets both can see rabbit now and have I seen the rabbit to true. He says the direction to the rabbit is I. I'm going to store that. And the distance to rabbit is this much. This is predator code. This is code for a predator. You don't need, the praise code can be a lot simpler. It doesn't need to remember nearly as much. Okay? If I had seen the rabbit, then what I'm going to do is I'm going to move to his last known position. I'm going to say, if the distance to the rabbit is greater than 0, I'm going to lower that, and I'm going to try to move towards the rabbit. Okay? Return direction to the rabbit. Otherwise, if I lost the rabbit somehow, I said, okay, I can't see I don't know where the rabbit is anymore, set to false, and I'm going to pick a random direction to go. If I've not seen the rabbit at all, what I'm going to do is I've got this current direction that I choose initially. And essentially what I describe this is that this is a pacing motion that the fox does. It's going to pace back and forth. It's going to try to go straight if I can move in a direction. So that's a nice, useful function that you're going to be able to use. Can move. Given a direction, can I go in that direction, true or false? If you try to move in an invalid direction, like you can't move that way because there's a bush in the way, bushes block line of sight and movement, or there's a wall in the way, it's going to return false. If you try to go in an invalid direction, you're just going to stay put where you are. Okay? If I can't move in that direction, I'm going to try to go around it. And the way it tries to go around something presents the other really useful function for you to use. It uses can move model.turn. Model.turn says, given a current direction and a number, I'm going to turn a number of 45-degree turns equal to that number. So if current direction, and notice that we're not using north, south, east, west, or at all in this code, right? It's not saying if I'm trying to go north, try to go northeast. It's saying if current direction model.turn 1. Because otherwise you'd have 8 times as much code to write. So what this does is that if you give it 1, and this is ways north, then that 1 will give you northeast. 2 will give you east. 4 will give you directly away, south in this case. 6 will give you west. -2 will also give you west, by the way. And if you give it 14, which is 6 plus 8, it will also give you west. It handles the modular arithmetic for you, so you don't have to worry about that. Ain't that convenient? So it tries to go around there, and if it can't go around whatever it bumped into, like it's a wall or something, then it picks another direction at random to pace in. Okay? So that's essentially how that fox works. The end result is if it sees the rabbit, it tries to get to it. Now, there's generally 2 strategies of varying success that the students try to come up with. I'll go over the first one, which I consider harder and less successful generally. The first strategy you can use is you can attempt to kite the fox. For those of you who are familiar with MMORPGs, that probably makes total amount of sense, kiting the fox. For those of you who are unfamiliar with multiplayer games like World of Warcraft, kiting refers to a strategy in those games where a party attempts to take something down not by fighting it, but by having one player go, look at me, big ugly monster, chase me, eat me, and then run away from it, while everybody else basically hits it with damage over time spells or something like that, or poison effects. Basically trying to whittle this thing down over time in a game of attrition rather than trying to just simply beat it outright. It's a very successful strategy and for some bosses, and can be safer if you've got a very skilled kiter. So basically, this would be simply to say, and this would ostensibly possibly work for the rabbit because guess what? You move at the same speed as the fox. So as long as you can stay one move ahead of the fox, awesome, you can't get eaten. This often involves, I've seen strategies involve like a rabbit finding a bush and then basically running around the bush once the fox locks onto it, because you just basically get locked in the same sequence of moves at that point, and then you can kind of run out the clock that way. This is much more difficult than the other strategy I like to do, which is, and that involves, is there not an app installed in this? Paint then, fine. Okay. So the other way to do this is to use the fact that we are dealing with line of sight over here. Okay? When the fox looks for a rabbit, it's going to be sending out these, it's going to be sending out these yellow beams representing its line of sight. Right, and I'll just draw a few. And I'm going to shade this in here. This blue area, that is a huge honkin' blind spot, right? It can only see in straight lines, according to the grid. So the strategy that I suggest you use, which is probably the simplest strategy to get a fairly high grade, is you stay put until you see the fox. Just simply don't move. You're hiding. It's a good strategy that prey animals use all the time, right? And then if you see the fox, well, your hiding place sucks then. So move out of the way before he sees you. So, because the idea here is the fox is going to look, and then he's just going to move. If he doesn't see you, he's just going to move in a direction. Then it's your turn. And if you see the fox, well, he hasn't seen you yet because it's not his turn yet. So if you see him first, guess what? You can move out of his line of sight. And then he can't see you. This works extraordinarily well, this strategy. Just simply moving out of the line of sight of the fox. Now, your goal for the day, or besides getting set up, and I would say definitely for next lab, is where you want to be at minimum, is if you see the fox, move directly away from it. Otherwise, stay put. Now, directly away from it isn't a good strategy because that's still within line of sight, but it's easy to figure out. That's model.turn 4, right? That's 180 degrees. That's the opposite direction. So after that, you can start experimenting. But right now, you definitely want to get to the point of, if I see the fox, run away. Okay? So with that, I'm going to go ahead, let's go ahead and get you set up. Okay, we still got like half an hour-ish, so we're going to go around the room, help you get set up. By the way, this one, you are more than welcome to work with somebody else, not only work with someone else, but turn in the exact same homework as one other person in the class. In other words, you are allowed to pair program on this one, turn in the same assignment, demo together. Other assignments are going to be much more solo, but because not everybody necessarily brought a laptop this first lecture, this is why we do this. Mm-hmm. So you are more than welcome to do pair programming on this one, turn in the exact same homework as someone else, just simply come up together as a group, say you do it as you're doing it as a pair, okay? It also helps that we only have one section in this room.